As you might have noticed, in the last couple of years, BETA has started developing simulation solutions also in the electronic sectors. And I'm going to talk to you about, more specifically, our ECAD importer, which is a gateway to finite element analysis simulations for printed circuit boards. So first, I will talk a little bit about what ECAD is, what our ECAD importer does, what it can do for you, and then I will present you with a short walkthrough through the importer and a live demo. Finally, we will conclude with some application examples that can showcase the power of the tool. So let's go to the introduction. The ECAD importer was introduced as an ANSA plugin in version 21.1. And ECAD stands for Electronic CAD, and its applications are in design, fabrication, and simulation of printed circuit boards and electronics, which is crucial for lossless information flow between designers, manufacturers, and simulation engineers. So ECAD can contain many types of information like geometrical, electrical, topological, physical, etc. And the purpose of the importer is to gather all these types of information and integrate it in an ANSA database so that we can generate an ANSA model from the ECAD that reflects all these properties of the model. The ECAD format that we have chosen to support is the IPC 2581 revision B, which has been chosen because it's an open source format. It's intelligent, so it contains interconnected multi-dimensional information. And it's supported by a large industrial consortium and most ECAD and EDA vendors. So the main features of our ECAD importer are the following. First of all, from a single ECAD file, you can produce models with 4 different levels of detail, according to the needs of your simulation, which do not depend on the solver. So our tool is solver agnostic. And also, it's easy to customize the import through a GUI wizard, and it's also easy to automate by using it in batch mode. Furthermore, the PCB stackup is editable during the import process, so you can change the thickness of layers, you can select layers, you can fuse layers. We can generate automatically batch meshing scenario, which is very important for automation later on. And the final model hierarchy at the end of the process is highly organized and structured. So we have all the PCB layers and vias in different parts. We have also grouped components in different parts. The electrical nets topology is reflected in the sets hierarchy of the model. We have different properties for conducting dielectric and packaging materials. And we have also facilitated the creation of connections between boards and components by putting the pins in the faces of the connections in the corresponding sets. So let me explain to you what I mean by levels of model detail. So as we said, we support 4 levels of detail. The first level is the homogeneous board. So the whole PCB is modeled like a homogeneous slab of material with no internal structure. The only thing you know is how much copper percentage is in this slab. The second level, each layer is a homogeneous layer of material. So you have 1 slab per layer, either electric or dielectric or conducting. And you can also drill the vias in this board. At level 3, you have full 2D metallization. So at this level, all the dielectric layers are homogeneous slabs of material, and the conducting layers are infinitely thin 2D faces, which carry all the exact geometrical information about the conducting geometry of the PCB as included in the ECAD. And finally, the level 4 is the full 3D metallization level, which is very similar to level 3, but the only difference is that the Z level, so the height of the conducting layers, has been moved according to the thickness of these layers, so that at the later stage, at the mesh stage, you can extrude layered mesh from the conducting faces in order to create thick metallization at the mesh level. So let me show you in brief how the workflow of the ECAD import is. First of all, we have 5 common steps. So you have to select the level of detail you want for your model. Then you have to select the IPC file you want to read, which is an XML file. Then you preview the stackup and you can edit it optionally. After that, you can import the 2D features that bound the conducting features of the PCB. And then you create the PCB profile itself. Then, according to what level of detail you have chosen, there are some level-specific steps. So you branch into different steps according to the level of detail. And finally, the whole workflow reunites again for 2 final steps, which are both optional. The one step is to import the components of the PCB. And the last optional step is to generate automatically batch meshing scenarios. So let me now go over to the live demo. Krisha, can you see my answer screen?
That's right. I confirm that we can see you lively demonstrating the ECAD importer. Christos, thank you.
Okay, thank you. So we go to ANSA to plugins, and we call the plugin from the menu through the ECAD importer plugin. And we are presented with the first screen that prompts us to select the level of detail. And you have 3 blocks of option. The first block corresponds to the levels of detail I have told you before, the 4 different levels of detail for the board. The second group of options concerns whether you want to drill vias or not. And the third group of options concerns the components. So whether you want to import components and whether you want these components to have pins. Because of time limitations, I will show you only one of the levels of detail, and for the rest, I can show you some readily prepared models. So let's choose the most high level of detail, the full 3D metallization, and let's import components. So let us open a new IPC file. This is an XML file of standard format. So we load this file and we get a message that this is a valid IPC file. At the next stage, we get a preview of the StackUp as it is contained in the ECAD file. And we can have the preview in 5 columns. So the first column is a column of checkboxes, which you can use to select which layers to import and which to ignore. For example, if you want to ignore these 2 layers, you can just deselect them. And if you choose Accept StackUp, you can see that these 2 layers have vanished from the StackUp. Let's undo this by clicking on Undo. Then you have the layer name, the functionality of the layer, the thickness of the layer in microns, and the material. And the color signifies the functionality. So if it's red or yellow, it's copper, and if it's green, it's dielectric. Furthermore, you can edit the thickness of each layer by clicking on Edit Layer Thickness, and then this column can be edited. For example, if you want, instead of 25, you want 20 microns, you can edit it. And there is a final option to fuse layers that are conducting layers that are separated by infinitely or very thin dielectric layers. So sometimes these dielectric layers have 0 thickness or a very small thickness, like say 0.5 microns, and this means that they are not meant to be actually constructed, so they can be neglected. And the adjacent metallic layers can be fused if this thickness is below this number in this box. So if you accept this, then you can see that this dielectric layer has vanished, and the 2 adjacent layers have been fused into a single layer. But for now, let's go for the original StackUp, and let's go to the next page. So here we will import the 2D curves that bound the conducting geometry. And we have a group of basic options and a group of advanced options. I won't go into the advanced options because we have some time limitations, but I will explain the basics options. So first of all, you can select the resolution in microns, which affects effectively the mesh target length. And then you have 2 options about importing or not importing features without finite. So features without electrical topology, which are usually either descriptive elements or mechanical engineering elements. So if you want all of these features imported, you click on Import this, all features without finite. If you just want the holes that are mechanical to be imported, you can click on this button. And to show you what I mean, I go back to my presentation and I will show you. In this slide on the left side, we can see highlighted with white all the elements of this PCB that are non-electrical elements. So you can choose to ignore them or import them. Or optionally, you can choose to import only the mechanical holes and vias, which is the round circles highlighted in white that are on the right side of this picture. And finally, there is a third option to ignore all the features that lie outside of the PCB profile. So in my next slide, you can see that the PCB profile is this curve highlighted in white, and there are some features that lie outside of this white profile. So in the 3D model, they will not play any role. So you can choose to ignore them to make the procedure faster. So you can see that these yellow letters fall outside the profile, and you can choose to not import them. So let's go with these options, and let's import the features. So now each layer is imported, and the curves of each layer are positioned on the right height. So in the end, you can see that you have all the curves for all the layers positioned at the right Z coordinate, as you can see here. So at the next stage, we can go on and import the PCB profile. And here you have three options. First of all, you can import the profile geometry contained in the IPC file, which is the native profile that you have in your IPC file. And here we can see now that the bounding faces of the PCB are created. So this is the volume in which the PCB lives, so to say. So you have both the layer interfaces and the lateral faces that bound the PCB. And there is also another option. You can you can undo this, and you can use a bounding box of all these curves with a margin that can be determined from this box expansion coefficient in percentage here. So if you use a bounding box, this is just a simple rectangular box that bounds all the curves of the PCB. So here you can see that you have a very simple rectangular box. And finally, let's undo this. You can also import custom curves. So you can draw the custom curves yourself, or you can even import them. Let's merge this file with another file, with a custom profile. Okay, now I have imported some extra curves. Let's isolate them. And I can choose these curves for my boundary. So I say pick curves. I choose all these curves. And I get a message that the curves are valid, so I can apply the PCB profile. And now you can see that we have our custom profile. But let's go now with the original profile. So this is the original profile, and let's go to the next step, which is the 2D topology step. So at this step, the conducting geometry of the board is going to be created. And there are two options. There is the fast 2D topology, which accelerates the procedure very much. But sometimes if there are short circuits among finites, so electrical nets, this option can fail. So in this case, you have to deactivate it and go for the other option, the acceleration by fusing features of the same finite, which I recommend to leave on, except if you see other problems, which is very rare, then you could also deactivate this, and then this is the slowest import you can get. So this stage is usually the main bottleneck of the import. It lasts the longest. But for this PCB, it takes a little less than half a minute. And at the end, you will have at each level the 2D metallic faces that represent the conducting geometry. So until this is finished, let me show you an example of how a level 2 model would look like. So here we have a level 2 model. Here we have the components. Let's hide the components. And here we have the board, which is, as you can see, a homogeneous board, a homogeneous layered board. So each layer is a homogeneous slab of material, as you can see here. We don't have any metallic features. We have only holes. But we can see how much copper is contained in each layer by going to layers and clicking on each layer group and going to the user attributes where there is a metal fraction attribute. So this layer contains, for example, here 8.87% copper, or this contains 74% copper. So let's go back to our model. It should be ready by now. Yes, you get a summary of the success of the procedure. So all layers have been created successfully. As you can see here now, all the metallic faces have been created. So let's go to the next stage, which is to drill the board to create the 3D topology of the board. So in this step, we drill all the layers of the board, and in the drilled holes, we place cylinders, which are connecting all the layers mechanically and electrically to each other. And these cylinders are called in the technical jargon vias. So this step is usually faster than the 2D topology. And we can have both conducting and non-conducting vias. So they have a different property. Conducting vias have yellow color property, and non-conducting vias have a purple one. So now the model is been drilled, and you can see how it looks like here. So there are holes going through all the layers that connect all the layers together. And then we go to the import PCB components step, where we get a preview of what packages exist actually in this PCB, the first column. There may occur, these packages may occur more than one time. So occurrences, we have the number of times these packages occur. We have the number of pins for each package, and we have two columns that can be edited. The one column is called thickness. It's the thickness of the package, and the other column is the standoff. So it's the distance of the component from the board. And you can edit both these columns, or you can even put a uniform standoff if you put a number here for your components. And if I import my components now, you will see the final result. So, as you can see, I have now imported all my components on both sides of the PCB. So, at the next stage, we have the batch meshing scenario. In the meanwhile, let me load a full 3D mesh to show you how a full 3D mesh would look like in this case. So, in this case, you can create automatically batch meshing scenario, and you have these options here. First of all, you can select the target length of your mesh. Then you can select the number of mesh layers for thick conductors. So how many layers will the layered mesh of the thick metallization have? The default is 1. And you can also choose to create volume scenario. So if you click on this button, then you have automatically created all the batch meshing scenario you need for meshing this model. And now we're finished, and we can take a look at the model. So let's have a brief look at the structure of this model. First of all, we have a structure in parts. So sorry, not in properties, in parts. So we have one group for layers. So you can isolate specific layers for viewing here. You can also isolate the lateral boundaries of the board. You can isolate the vias of the board. And you can also isolate the components, which are grouped in top components and bottom components. So let's show only the bottom components. And you can also isolate a single component. So here we have a component which has 2 pins, and its property, the body property is different than the pin property. Then we have the property data structure. So as I told you, the PEC property is the property of the conducting bias, as you can see. The lateral property is the property of the lateral faces that bound the PCB. Then you have the conductors on each layer, which have different material properties and the correct thickness in microns. You have properties for the dielectric interfaces between the layers. And you have, for the component pins, you have, according to their type, you have different properties if they are through-hole components or SMD components. And for each specific type of package, you have a different property. So, for example, these 4 components have the same, are of the same package. That's why they have the same property. And finally, we have a set structure, which reflects the electrical topology. So under FiNet, you have all the electrical nets of this circuit, of this PCB, and you can isolate a specific net, a specific circuit for viewing and for editing, of course. And you can further subdivide it in top and bottom and other layer components. And finally, we have a group here called component pins, which contains all the pins grouped in layers. So for example, this group contains all the pins of the top layer. And furthermore, they are subdivided, for example, in components. So these are the pins on the top layer that correspond to the capacitor C7. So you have the pins of the capacitor are the brownish ones, and the yellow faces are the faces where the connections have to happen on the top layer in order to connect the capacitor with the board. And we leave it to the user to decide what kind of connections he wants to have. And so this is roughly the database structure. Let me show you the batch meshing scenario, which are divided into shell mesh batch meshing scenarios, thick metallization for the layered mesh on the coppers, and dielectric volumes. And in order to view the mesh better, let me show you this model. So this is a full mesh of this PCB. We have performed all the meshing through the batch mesher, and with the exception of the components which have been meshed by the map block feature of ANSA. So you can see here that the components have been meshed by map block, and all the rest has been meshed with either layered mesh for the thick metallization, tria mesh for the shell mesh, and unstructured tetra mesh for the volumes between the conducting layers. So here you can see that there is thick metallization inside these layers, and the vias have been also meshed. So let me now go to the applications. We have performed two groups of applications in order to showcase the power of this tool. The first group is about thermal simulations, and the second about structural simulations. So about thermal simulations, very significant source of failure for PCB and electronics is thermal failure because of overheating of components, and it's very important to calculate the temperature of the components. So here we have performed a steady-state conduction simulation. We have placed a constant uniform heat source on the largest components of this PCB, and we had conduction in solids and a forced air convection boundary condition on the surface of the PCB. This model is tetra meshed for the dielectric layers and shell meshed for the conductors. We had a total heat load of 20 watts, and we have solved this in Nastran, and the results are in Kelvin. And on the right, you can see the final temperature on the surface of the board after a steady state has been reached. And in the next slide, you can see temperature distribution on two different layers. So on the left, you have the temperature distribution on the top layer, and on the right, you have the temperature distribution on the ground plane. And you can see how the metallization of the ground plane affects the distribution of the heat, not only on the ground plane, but also on the top layer. Next, we have performed a thermal integrity analysis with CFD. So we had a CFD conjugate heat transfer simulation. So we enclosed the PCB in a casing with two air inlets and one outlet. As you can see on the right, there are two rectangular slotted openings for letting air in, and one circular opening for letting the hot air out. And we have cold air floating in. So we have uniform heat generation in all components. We have a tetra mesh for the dielectrics and shell mesh for the conductors, and 7 million shell elements for the mesh and 82 million solid elements. So we have used ANSYS Fluent as a solver. And on the left, you can see the temperature distribution on the casing of this PCB. And on the right, we have removed the casing to see the temperature distribution on the PCB itself. And furthermore, you can perform cuts, and you can see on the left a temperature cut where you can see the cold air flowing in through the inlets and getting gradually warmer as it flows over the hot components. And on the left, on the right, you can see the velocity cut with inverted colors because the cool air that flows in is also the fastest. And then you can also plot the streamlines of the air flowing through the PCB. Another application is structural integrity for PCB soldering. So when you solder a PCB, you put solder paste on the components and on the PCB, and you put it in the oven. You heat it up so that the solder paste melts. And then later on, you turn off the heat, and the solder paste, the molten solder paste, starts to solidify and connect the components to the board. But because the thermal coefficients of the board and the components is different, they contract differently, and so the board starts to warp. So we have started here at a peak temperature of 227 degrees Celsius, and we have stopped at a room temperature of 27 Celsius. And we have calculated the warping. So in this picture, you can see how warped at the final stage the PCB is. We have exaggerated the deformation by 20 times, and we have solved this in Nastran. And in the next slide, you can see the actual displacements on the left in millimeters, and the stresses that are induced on the components because of this warping. So this is important to know if your components will fail, maybe because of excessive warping. Another structural integrity application is random vibrations. So the second most important reason for PCB and electronic failures is vibrations. So for this case, we have taken the same PCB and we have performed a model analysis. We have computed, first of all the modes up to a certain frequency. You can see here the first mode, left is the deformation of the mode, and on the right are the stresses of this mode. We have performed the simulation in Nastran with shell mesh for conductors and solid mesh for plastic. And at the next stage, for each frequency in this spectrum from 20 hertz to 2 kilohertz, we calculate the model response. So we calculate the stresses at each separate frequency. And finally,
Christos, I'm really sorry. I'm in the awkward position to just inform you that we are already through the Q&A session. So probably in case our participants would like to raise questions right after the end, maybe it would be better to start summing up. Thank you very much. Although you are the last session for today, to make sure that everyone will be still present for the questions. Thank you very much.
Of course, this is the almost the last thing I want to say. So you have on the right, you have the random vibration result. And finally, the final application is the structural integrity test, where we have dropped the PCB in a case. And you can see the time we have solved this model in Abaqus, and you can see the stresses on the casing and on the PCB at the moment where it hits the ground. So you can see where the most danger for the PCB components exists. So this concludes my presentation, and I'm ready to take your questions.